I will walk you through the full kinematic analysis of this mechanism that we started working on in class last Thursday. So if you look at this mechanism, you can see that we have two sliders, and one slider is actually moving on a link that is itself rotating with respect to the 0th frame or the world frame. So this is a pretty complicated mechanism, at least as far as planar mechanisms go. This is pretty complicated. We already have gone through this position level analysis of this mechanism, but let's briefly repeat that and spend most of our time on the velocity and acceleration level analysis. And hopefully, after I'm done with writing, I will also make append to this video the numerical calculation part, essentially the MATLAB part of solving this problem. So stay tuned for that. Okay, anyway, so in order to, let's go to deriving the equations that we would like to put into MATLAB. So I hope I defined the angles just like we did in class. So if you remember, we defined theta 1 to be the angle between y0 and y1, where y1 is the axis that goes along O1 to C, is a unit vector along O1 to C. So the first set of axes x1, y1, z1 are fixed on the first link. Here, this is the first link. The second link is over here, and the second set of axes x2, y2, z2 are fixed on the second link. The third set of axes are fixed on the third link. Fourth are fixed on this fourth link. Fifth are fixed on the fifth link. So you can see how I assigned the axes, and they are in the blue color. And with these definitions of the angles, we came up with the rotation matrices between the various frames 1, 2, 3, 4, 5, and 0th frame. I have recorded them over here. If you check that out, the rotation matrix between 0 and 1 is given by a rotation about the z-axis. All of the frames' z-axes are the same. They share a z-axis. So essentially, R01 is the rotation about the z-axis by an amount theta 1, and we know that the matrix that corresponds to that rotation is given by this one right there. R02 is a rotation about the z-axis by theta 2. R03 is a rotation about the z-axis by theta 3. R04, which is the rotation matrix of the slider, a fourth link, which is a slider, with respect to the 0th frame, is actually equal to R01 because the fourth link rotates exactly in the same way as the first link rotates. Indeed, it is a link that slides on the first link, so it must rotate the same way. R05, on the other hand, the fifth set of axes look exactly in the same direction as the 0th axis. So R05 is the identity matrix. There is no rotation of the fifth frame with respect to the 0th frame. It just translates. Okay. So far so good. If you look at what are given to us and what our unknowns are, I have summarized them on the left-hand side of this page. Of course, the link lengths are given to us. The length from O1 to O2 is 300 millimeters. I assigned it the letter A0. I assigned the letter A1 to the distance from O1 to C, which is the length of the first link. It is 400 millimeters. I assigned the letter A2, or the symbol A2, I should say, to the link length O2 to B, which is the link length of the second link. It is 150 millimeters. The length of the link 3, which is the length of the vector that goes from C to D, I assigned that the symbol A3, and that is 160 millimeters. The knowns are the angle singular angle theta 2, which is 135 degrees. Theta 2 is here. We know its rate of change, the first derivative, which is 500 radians per second. And even though the question doesn't give this as a known, because it is not asking the acceleration level analysis, since we are planning to go through the acceleration level analysis as well, I assigned another known for us, which is the second derivative, second time derivative of theta 2. I set that equal to 1500 radians per second. And depending on what level of kinematic analysis we're performing, that we have a few unknowns. So if you're only doing the position level analysis, we are only looking for theta 1, theta 3, d4, and d5, where d4 is the distance from O1 to B, from here to right there, along the y1 axis. And d5 is the distance between O2 to D along the x0 axis. So let's see. I should say it's the distance from D to O2 along the O2 axis. There's no O2 axis. Let me repeat that. D5 is the distance from D to O2 along the x0 axis. Okay. If we're doing the velocity level analysis, essentially we're looking for the rate of change of these variables: theta 1 dot, theta 3 dot, d4 dot, and d5 dot. And if we're doing acceleration level analysis, we're looking for the double time derivatives of these variables: theta 1 double dot, theta 3 double dot, d4 double dot, and d5 double dot. Okay. Once we set the problem up like this, the first task that we have, of course, is to write loop equations, because you can see that this one is a closed loop mechanism, since every link is connected to at least two other links. So we actually did that in class, but since I don't remember it, I'm going to do it again. So if you remember, I believe we had two loops. I mean, I don't not remember it totally. I remember parts of it, but not exactly, I guess. Okay, so I will let's see. The loops that we wrote, right? The loops that we wrote look like loop 1 was going from O1 to B to O2 back to O1. That was loop 1. Loop 2 was going from O1 to C, C to D, D to O2, back to O1. Okay, and let me actually move these over here, right there. And in terms of position vectors between frames, we could express these as, let's look at loop 1. Position vector from O1 to B is actually the position vector from the origin of the 0th frame to the origin of the 4th frame. Position vector from B to O2 is equal to the position vector from the origin of the 4th frame to the origin of the 2nd frame, plus position vector from O1 to O1 is the position vector from the 2nd frame, origin of the 2nd frame, to the origin of the 0th frame, and this is equal to 0. This is the first loop equation. The second loop equation, the vector from O1 to C is the position vector from 0 to 3, plus position vector from C to D is P sub 3, 5, plus vector from D to O2 is P 5, 2, plus P 2, 0 equals 0. Okay, very good. And then we went ahead and expressed these in the 0th frame, which went something like So let's do loop 1 first. P04 is L1 in the x1 direction. Sorry, not L1, I'm sorry. It's A1 in the, it's not even A1. Let me just see. It is D4, because D4 is a distance from O1 to B. It is D4 in the Y1 direction, actually. And if you write the Y1, if you look at the Y1 direction written in the X0, Y0, Z0 frame, it will be the second column of the R01 matrix. So P04, let us look at the loop equation first. So this is going to be D4 times minus sine theta 1, cosine theta 1, and 0. This is P04 plus, oh, sorry, okay, P42 is going to be A2 in the minus Y2 direction, as you can see from the figure. A2 is the distance from O2 to B, O2 to B. But you want to go from B to O2, so it's in the negative direction of Y2. So this is going to be minus A2 times Y2, but Y2 we can read it off. But you know, the components of Y2 can be read off from the second column of the R02 matrix. So this is going to be minus A2 times minus sine 2, cosine 2, and 0. Very good. Okay, so finally P20, which is in the negative Y2 direction, and the amount that we have to go is A0. It's going to be negative A0 in the 0, 1, 0 direction. And if you recall, we said this whole thing was P42, and this whole thing is P2, whoops, P20, and we're summing these, is equal to 0. Okay, and our second loop equation, you have to go from 0 to 3 first, which is from O1 to C. That is in the Y1 direction, and the distance we have to go is equal to what? A1. So this is going to be A1 minus sine 1, cosine 1, and 0. Then 3 to 5, which is the vector from C to D, that's in the negative x3 direction, And the amount we have to go is A3. So it is negative A3, and we read off the components of the x3 direction from the first column of the matrix R03. That looks like cosine 3, sine 3, 0. So again, let me record these. This is P03. This whole thing here from here is P35. The vector from 5 to 2, the origin of the fifth frame, to the origin of the second frame, has a distance d5. That's what we just assigned. The distance is d5, and it is in the positive x0 direction. So we have to write here plus d5 0, 0. This is P52. And finally, we've already determined what P20 was in the first loop equation, because we used it as its last term. And we just record that here immediately. To get something like this. This is P20. And we're adding these. Oops. Equals 0. So here are our position level loop equations 1 and 2 in coordinate form. We then plug these into Newton-Raphson algorithm that we coded in MATLAB and found the solution. I will end the first part of the video here. This covers the position level analysis part, and in the next video coming up, I will concentrate on the velocity level analysis. Actually, I will first provide you the solution to the position level equations. That is, I will give you what the values of theta 1, theta 3, d4, and d5 are when theta 2 is equal to 135 degrees. And then derive the velocity level loop equations, and then use these the results from position level equations to derive what the values of theta 1 dot, theta 3 dot, d4 dot, and d5 dot are. All right, see you in the next video.